Right. See, biomolecules mainly deals with different types of functional groups, aldehydes, amines, carboxylic acid, or mix of those three.
Hmm.
There are many types of biomolecules that includes carbohydrates, proteins, nucleic acids, lipids, fats, vitamins, hormones. These are all biomolecules. We use the term biomolecules because they are observed in living systems.
Hmm.
Okay? So the first thing we will start off with is carbohydrates. Okay. The old definition of carbohydrate was it is about hydrates of carbon, which means if you have X number of carbons, there may be Y number of water molecules connected to it. If you have this ratio, a simple ratio of X and Y, that means they are carbohydrates. This was the old definition. There are definitely certain molecules which will fit in this definition that includes glucose, fructose, sucrose, and so. So you can see C6H2O6. Okay, because glucose and fructose are actually C6H12O6 form. Correct. Similarly, sucrose. Sucrose is C12H22O11. Okay. So this is also fitting into that definition. But then acetic acid, although it is not a carbohydrate, but yet it does fit in the definition of it. That is C2H2O twice. So although it is not a carbohydrate, still it is fitting into the definition of carbohydrate. Okay.
Yeah.
Next is formaldehyde. That includes C1 and H2O1. Here, this is also not a carbohydrate. Okay. There are certain carbohydrates which may not fit into this definition also. For example, rhamnose. Rhamnose is C6H12O5, but it is not fitting into the definition of the hydrate of carbons. But it is a but it is a carbohydrate. Same goes with deoxyribose. Okay. It does not have the exact simple ratio of carbon and water molecules, but yet it is a carbohydrate. And this is where the new definition, which is the modified definition of the old one, was given, which implies any optically active polyhydroxyaldehydes are ketones. That means there has to be aldehyde or a keto group, and there has to be polyhydroxy. That means more than one hydroxy group should be present.
Sir, I have to open the door.
Yeah,
Just
yeah,
one
sure,
moment.
sure.
Sir,
So as per the definition, if you have an optically active compound, which is polyhydroxy, either it should be an aldehyde or a ketone, then they are called as carbohydrates. Correct? Now, you might have a molecule which might be existing in the form of a dimer or a polymer, which on hydrolysis should also produce a polyhydroxy aldehydes or ketones.
hmm.
So such kind of compounds are called carbohydrates. Out of the carbohydrates which we know, glucose and fructose are most used and very commonly used carbohydrates everywhere. So its structure, how it is, that is more important for us. These are more like simple objective type questions. Check it out. Glucose, which is C6H12O6, it would have 5 hydroxy groups on it. For example, if you take this carbons, there are total of 6 carbons, 1, 2, 3, 4, 5, 6. The first carbon will have an aldehydic form. Next, second, third, fourth, fifth, and sixth, all of them have one OH group on it.
Hmm.
So there are 5 hydroxy groups on it. Then, because it is optically active, in the polarimeter, it will give a dextro rotation. That's why this positive value, which means it is dextro rotation. The angle of rotation which you will see it on the polarimeter is 57.2.
So
And
what is dextro rotation? Can you like explain that?
what is dextrorotation?
Mm.
Okay. Now, to brief you something about optical activity, do you remember this part or no? Or should I
Yes, sir,
repeat
I
that?
know.
What is, when it comes to glucose, I told you, it is dextrorotatory with an angle of 57.2 degrees here.
Mm.
Glucose has this particular structure wherein you notice that second, third, fourth, fifth carbon, these have four different groups on it. So hence they are chiral centers.
Yeah.
So this is a chiral center because it has 1, 2, 3, and 4. This entire thing is 4. There are 4 different groups on it. Clear? So when you have a chiral center, you can give an absolute configuration associated with it.
Mm.
And our absolute configurations are R and S. Okay. Let me remind you what are R and S here. Okay. Suppose if you have chiral center here, chiral center should have 4 different groups, let's say A, B, C, D, or 4 different groups. Got it?
Mm.
Then, because it is a tetrahedral molecule, how does it look like? Tetrahedral molecule typically looks like this. Got it?
Yeah.
Where, if you notice, let's say here we have, A, B, C, and D. Just for the sake of example, I'm writing it. Let me remove this part here. Okay. This is the three-dimensional structure, how it looks like. Got it?
Yes.
Now, to express that it has some configuration, that means because of its chirality, there might be some amount of angle which might be deflecting for plane polarized light. Got it?
Yeah.
So to represent that, what we do, we will convert this into something called a Fisher projection. Fisher projection, correct? What is Fisher projection exactly? Fisher projection is something like a top view of a molecule. Or in the other words, suppose if at all I start viewing the molecule from this end, like this, okay? When I start watching the molecule from this end, I will notice that these two groups are coming towards me like this, isn't it?
Mm.
Okay, they are like this towards me. And A and B groups will be away from me and they look vertical.
Yeah.
These two look horizontal while these two look vertical.
Mm.
Got it?
Yeah.
So in that case, write a vertical line and a horizontal line first, this way, the cross. And
Right.
on a vertical line, A is above, B is below.
Mm.
And on the horizontal line, it is
The
as if you are standing on this end and then watching the molecule.
Mm.
When you are watching the molecule, you know that this group is coming out of the board. You are on the board. Imagine you are on the board here, exactly on the
Yeah.
board, and B is coming out of the board, C is going inside the board. So you're exactly on the board here. So on the right hand side, what do we see?
See.
Here. On the left hand side, D.
The This is
Okay.
front view.
So therefore, left side it will be D, right side it will be C. Correct?
Mm.
This representation is what we call it as the Fisher projection. And on the Fisher projection, we will give a ranking system.
Yeah.
We will have to give a ranking system. Now, let's say here, if you notice, if this compound has A, C, B, D here, okay? Now, in that case, suppose if I give you different rankings here, let's say I have 1, 2, 3, and 4. These are the ranks I have given, okay? Ranking as in priority here. I have given a priority to groups. Then what you need to do, you need to check where exactly is the least priority group. The least priority group, where is it? Here,
Yeah.
correct? it is on horizontal line, correct?
Hmm.
If the least priority group is on the horizontal line, right? If the least priority is on the horizontal line, then you need to check how the 1, 2, 3 groups are present. Now notice if 1, 2, 3 are, you know, observed in a clockwise direction, correct? So here it is conditional with least priority group, with least priority group on horizontal line. Then in that case, clockwise rotation of 1 to 2 to 3 group represents S rotation. Okay,
Hmm.
this is called S configuration. And counterclockwise counterclockwise rotation of 1, 2, 3, if you observe, it is called R configuration. So in this case, it is 1, 2, 3 going this way. So what will this be? So this chiral center is R configured, sorry,
Hmm.
S configured, because it is going clockwise. So it should be S configured.
Yeah.
Clear? On similar lines, imagine I take one more group here, wherein, let's say, I have a ranking
One
system here.
second.
Hmm?
How is counterclockwise also 1, 2, 3?
No, I'm saying if counterclockwise,
Hmm.
if you are looking 1, 2, 3, and it is moving counterclockwise.
Oh, अच्छा.
For instance, here, if you notice, I have, let's say, A here, B here, C here, and D here. Okay. Ranking wise, we gave this as 1, 2, 3, and 4, correct?
Hmm.
Which means if you have least priority group, if the least priority group is on vertical line, if it is
Hmm.
on vertical line, then clockwise rotation will be R and anti-clockwise rotation will be S. Got it?
Oh, okay.
Hmm. Now notice how, hold this fourth and then see how 1, 2, 3 are rotating. See 1, 2, 3. How is it rotating? Anti-clockwise or counterclockwise. So that means it is still S configured. Clear?
Okay.
Likewise, if at all I have anything similar to it, so here I change it as B here, C here, and D here. Correct? So in that
Hmm.
case, this is priority 1, 2, 3, and 4. Again, the least priority is on the vertical line. So if I get clockwise, that means it is R configured. So this chiral center is R configured. Got it?
Okay.
Is that making sense?
Yes, sir.
So wherever there is a chiral center, we should be able to give a configuration associated with it. Okay, either it will be R configuration or it could be S configuration. Okay, how do we decide priority? Priority or ranking system is decided based on CIP rules. In simple sense, the first connecting carbon, or sorry, connecting atom, first connecting atom to chiral center to be compared, that need to be compared. Okay,
Yeah.
based on molar mass. Whichever has the highest molar mass, will get high priority. Highest molar mass or atomic mass, high priority.
Mm.
Done. So in simple terms, let's say if at all I have methyl here, OH here, I have CH2, CH3 here, and I have NH2 here. Got it? Sorry, here not methyl, hydrogen. Let's say I have hydrogen here. So what do? You compare the first atom here. So here carbon, nitrogen, oxygen, hydrogen. Based on that, you write the priority. What should be the priority now? Highest will be for oxygen,
Mm.
then nitrogen, then carbon, then comes
Then
hydrogen.
hydrogen.
Then now you
Yes,
know
sir.
the least priority group is on the vertical line. So now when you notice 1, 2, 3, it is rotating clockwise. So what is this one? R configured
Mm.
chiral center. That's how you decide it. Okay.
Okay.
The second rule is if, okay, connecting atoms, first connecting atom is same, then keep moving till the point of difference is observed. So that means you have to keep moving till there is a point of difference that you will be able to observe. In
Mm.
simple terms, let's say I take with an example here. I have CH3, C2H5, OH, and H. Okay.
Mm.
Now here, methyl will have this way. This is methyl. Hmm?
Yeah.
And ethyl will have like this. H, 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 and H. Okay.
Mm.
So compare this. First, when you compare carbon and carbon, they are same.
Yeah.
Then you say to carbon, which is the next element which is connected. Okay. Okay. Which atom is connected, which has, higher priority between here, between these three, all of them are hydrogens only. So you will take this hydrogen and then compare with whatever the highest atom that is connected to this carbon. Hydrogen, carbon, hydrogen. Which is the next highest atom? Carbon, right?
Mm.
Now you compare these two between carbon and hydrogen. Which one should be given priority? Obviously,
Carbon.
carbon. So this will become the
Mm.
priority group. Understood? That's
Yes,
how
sir.
point of difference should be checked. So therefore, first will be this one, second will be this one, third will be this one, fourth will be this one by priority. Correct?
Yeah.
So now notice how 1, 2, 3 is moving, beta. 1, 2, 3 is moving anti-clockwise, keeping the least priority on the horizontal position. So what should this be? R configured.
Yeah.
Done now?
Yes, sir.
This is how the Fisher projections need to be predicted. Clear?
Okay.
While writing Fisher projection, there is one thing that you need to keep common. You might see, sir, why we have to view it from this end? I could stand here and view and still get the similar type of structure, correct?
Mm.
Now, as per Fisher projection, one thing we should need to check is that horizontal groups, horizontal line groups must point towards the viewer, okay? And
Mm.
vertical line groups must point away from the viewer. Got it?
Yes,
That
sir.
need to be taken care. So that means these two should be towards you and these two should be away from you. Clear? So I think this is the basic idea that you need to have for checking out all the chiral centers here. Now notice the same thing here. Second, it is a chiral center, it is R configured. Next one is S configured, then R and R configured. So there are four chiral centers in glucose. R, S, R, R is the configuration. Got it?
Yes, sir.
And this group is called as D-glucose. Okay, what is that capital D? I'll come to that. But this capital D is something different compared to what is small d or plus. Okay,
Mm.
this is the structure of glucose. Now, if this is a capital D glucose, exactly if you take its mirror image, that will become capital L glucose. Okay,
Yes, sir.
two two optically active compounds which are mirror images of each other, they are called enantiomers. So D glucose and L glucose are enantiomers of each other.
Mm.
If at all I have to write the IUPAC name for glucose, what do we give? First, notice what is the main functional group here. It is an aldehyde. So you
Yeah.
will get a al, and you have 6 carbons. So it will become hexanal.
Yeah.
And second, third, fourth, fifth position, what is its configuration must be mentioned first.
Mm.
So it is 2R, 3S, 4R, 5R. Then
Mm.
2, 3, 4, 5, 6, and all 5 of them, we have a pentahydroxy group, and
Yeah.
it is hexanal molecule. Done. So this is the IUPAC name of glucose.
Okay.
Which glucose? D-glucose. Okay,
Or else it will be different.
correct. So if at all I ask you capital L glucose, you will write all these configurations exactly ulta.
Yeah.
You will write it as 2S, 3R, 4S, 5S, and then accordingly you will write down this IUPAC name. Got it?
Okay.
Now what does this capital D exactly represent? See, all the carbohydrates are assumed to be like a derivatives of a particular main carbohydrate or the primary carbohydrate. The primary carbohydrate from where we can keep producing multiple carbohydrates is glyceraldehyde, because you cannot imagine a carbohydrate which is lesser than 3 carbons, because we need to, as per the definition, carbohydrates must be optically active. To showcase optically active, there must be at least 3 carbons here, and there
Mm.
should be 2 hydroxy groups. Minimum is 2 hydroxy groups here, and it should be aldehyde or a ketone. Correct? So
Yes,
this
sir.
becomes the basic structure, beta. From this glyceraldehyde structure, if you keep on adding multiple number of carbons, you will get various hydrocarbons, various carbohydrates. Okay. Now, notice this:
Mm.
glyceraldehyde being the basic carbohydrate or the least carbon carbohydrate. If the OH group is on the right hand side, then what will this do? If you notice the priority wise, this is priority 1, priority 2, and priority 3. How is it rotating? 1, 2, 3. It is rotating anti-clockwise. Anti-clockwise means
Yeah.
it is R rotation, because the least priority group is on the uh, horizontal line.
Mm.
And usually what happens, I would say it is 90 to 95% cases.
Mm.
90 to 95% cases, if you have single chiral center and if it is R configured, in if you take its solution and try to check how the plane polarized light rotates, it will always go for dextro rotation. So this is a dextro rotatory sugar. Okay,
Yeah. Okay.
it is a dextro rotatory sugar. That means it
Mm.
is giving a positive, or it will give you a positive rotation on the polarimeter. Correct.
Yes, sir.
Now, if you notice, glucose is what, it is like a glyceraldehyde original form, But I have introduced three more carbons here, isn't it? Because
Hmm.
this is an aldehyde, OH, H, and CH2OH. This is supposed to be glyceraldehyde. But in
Hmm.
between, I had one, two, three extra carbons. Understood? So it is like this. From glyceraldehyde, you start deriving multiple number of carbohydrates by adding one carbon each. So here, by adding three carbons, you have reached up to glucose. But notice, in this glucose structure, the OH is still on the right hand side from where it has started with, correct?
Hmm.
The last carbon, the last chiral carbon, in the last chiral carbon, if the OH group is on the right hand side, that means it is derived from a glyceraldehyde's dextrorotation. Understood?
Okay.
Hence, all the dextrorotatory glyceraldehyde forms from which the other sugars are being derived, we call them as capital D sugars. Okay.
Hmm.
You may have noticed glucon D, capital D.
Yeah.
Okay. Understood. So the D represents dextrorotation sugars. Got it?
Are we? Yes. So are we stuck on the same page?
Yeah.
Oh no.
So since this is the after probably a lot of time you are doing IUPAC, isomerism. That's why I'm going it very slow. So try to understand that carefully. So once you understand the structures, then it will become very easy afterwards. Okay?
Yeah. Is this chapter a lot of theory?
No. Mhm.
Oh, okay.
Hmm. Now notice this one. So this would be the glyceraldehyde form. Okay? Clear?
Yes, sir.
In this, the fifth carbon is what you will notice. If it is on the right hand side, then this is a capital D kind of sugar. So this is a capital D sugar. Clear? And if the OH is on the left hand side, it will become capital L sugar. Any doubt?
No, sir.
This is the structure of glucose. Please do remember that. Now, similarly, when it comes to fructose, fructose would have five OH groups. It is a ketonic family. It is also a D sugar, capital D sugar,
Hmm.
but it will be levorotatory overall. That means overall fructose, if you take it into the polarimeter, it will be levorotatory. Okay, just a second.
Hmm.
Right, beta, check it out. So we have fructose being levorotatory. The angle at which the rotation takes place for this is minus 92.7 degrees. I'm talking about the D fructose. If you take its mirror image, it will be exactly plus. Okay, mirror image will be always the exact positive rotation. Got it? So if this is D fructose, this will be L fructose. See, for whether it is capital D or capital L, you should always check out the last chiral center's OH group. If it is on the right hand side, it is D. If it is on the left hand side, it is L. Clear? Now, what will be the IUPAC name for this one? So there are again six carbons. This is a ketonic group. So it will be a one, hexone, correct? Hexanone. So one, three, four, five, six. All of them have pentahydroxy group. And there are three chiral centers, 3, 4, 5. On 3 position, we have S, 4R, 5R. This will be the IUPAC name, which is pentahydroxy 2-one. Shana, clear beta? Right. So this is something which I want you to practice for a minute. Okay. Now, let's see what is the classification of these sugars. Sugars can be classified based upon how many units they can be hydrolyzed into. Okay. For example, if you have a sugar which cannot be further hydrolyzed, right, then that is the monosaccharide. Okay, it cannot be further hydrolyzed. Usually they are sweet in taste. That's why glucose, fructose, they are usually very sweet in taste. They are water soluble. So glucose, fructose, mannose, galactose, sorry. Yeah, mannose, galactose, ribose, these are all monosaccharides. They cannot be further divided into small carbohydrates.
Um, so so
Hmm.
when these saccharides are in their like proper form,
Hmm.
are they like normal sugar? Do they look like that or
Normal
different?
sugar, what we eat is sucrose. Got it?
Hmm.
That's a combination of fructose and glucose. Okay.
So fructose cannot exist separately.
No, in grape juice, for example, grape usually has more fructose content as compared to sucrose. Okay.
No, no. What I'm asking is that like, can you separate fructose
Yes, we
from
can. We can.
something?
We can. In fact, we can get. On the counter, we can get fructose, glucose separately as well. Got it.
Oh, okay.
For example, corn typically gives more fructose than glucose.
Hmm.
Okay, like that. Hmm. Next is oligosaccharides. Oligosaccharides are, you know, saccharides which on hydrolysis give 2 to 10 monosaccharides.
Hmm.
It should be able to give 2 to 10 monosaccharides on hydrolysis. They will also usually, are sweet in taste and they are water soluble. Sucrose, lactose, maltose, these are the ones.
Hmm.
Lactose is mainly observed in milk,
Yeah.
maltose from malts, okay. Sucrose, we know that from sugars, okay, sugar cane and all. Third one is polysaccharides. This on hydrolysis will give you more than 10 units of monosaccharides. Generally, they are not sweet in taste. They are called non-sugars.
Hmm.
For example, starch. Starch will be a form of saccharide which is coming from n units of alpha glucose. What is
Okay.
alpha glucose? I'll discuss in detail. Okay.
Hmm.
Most of the plant-based foods, maybe potatoes or uh, rice, and they all usually have starch in it. Okay. While the tree barks and all the walls of plant cells, they are all made up of cellulose. So cellulose is some n units, of a
Yeah.
polymer from beta glucose. Then glycogen. Glycogen is
Hmm.
something like starch. It is similar to starch, but it is a little bit more complex of alpha glucose. So
Hmm.
more complex structures of alpha glucose will give you glycogen. Usually we find it in liver, okay, and animal food, that there will be more glycogen present in it. Okay. So this is the classification based upon how many number of saccharides we have. Clear?
Okay. Yeah.
Second classification is based on the functional groups. If sugars are aldehyde based, we call them as aldose. Ose is a
Oh.
word used for sugar,
Hmm.
and ald represents coming from aldehyde family. So these are aldose family, and then we will have ketose family. Okay.
Hmm.
So if you have a three carbons, like you see, which is making an ose, we can simply call it as aldo triose. So
Okay.
glyceraldehyde is an aldotriose family.
Hmm.
Got it? Basically, it's an aldose family, and because there are three carbons, we call it as aldotriose.
Hmm.
Similarly, we can have any aldotriose here. This is also, same kind of aldose family. If at all we have a keto group, then we call it as ketotriose or ketotetrose or ketopentose and so on. Got it?
Yes, sir.
So fructose, for example, is a ketose. Glucose is an aldose.
Hmm.
Done. Now,
Yes,
just
sir.
now, I've explained you something about what is D and L configuration, capital D and capital L, correct?
Hmm.
When it comes to D-glyceraldehyde, if you notice 1, 2, 3, if it is rotating anti-clockwise this way, keeping the hydrogen at this position, which is on the fourth position, which is on the horizontal position, then the anti or the counterclockwise is always going to represent R configuration. And I told
Hmm.
you 90 to 90% of the time, R will always mimic with dextro rotation. Okay. So this molecule is in fact dextro rotatory, and anything that is derived out of it, they call it as capital D family. And if the OH is on the left hand side, we call it as capital L family. Okay.
Mm.
Now, what do you mean by derived? See, this is the family tree I'm talking about. Let us start with glyceraldehyde. This is the glyceraldehyde. Okay. This is like
Mm.
the great 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 grandfather. Correct.
Okay.
Somewhere from there it is derived. Imagine like that. Okay. As a
Mm.
history of family tree, if you notice. Correct. So from here, now it added, two sons or two, a daughter or one son, one daughter, anything like that. They have added two kids. So
Mm.
here is that one extra carbon. You can see this is one extra carbon, correct?
Yeah.
So this is like the family DNA that is always has to be restored here. Understood? Clear? So that is
Yeah.
still running in the molecule, except that we
Mm.
have some extra carbon onto it. Understood?
Yes.
So when you have four carbons here with two OH groups on the right hand side, then we call it as capital D erythrose. The name is erythrose. If the OH is on the left and the down OH is on the right, then it is called capital D threose. Now I'm only constrained to go for capital D glyceraldehyde family, not capital L glyceraldehyde. Okay.
Mm.
In that case, I got erythrose and threose. Again, if at all I add one more carbon, I'll get two more uh, two more children in it. So you can see up to this it was erythrose. Now I added one more with OH on the right hand side and OH on the left hand side. These are the only two possibilities, right? So when OH is on the right hand side, now what happens? All the OH will appear to be on the right hand side in the Fischer projection, and that would be called as ribose. So it is D-ribose. Okay. And if I keep one OH on the left, that will become D-arabinose. So one is D-ribose, the other one is D-arabinose. Okay.
Okay.
While here, when it comes to D-threose, if at all I add one OH on the right and one OH on the left, the one which you added on the right, that makes it like some kind of an alternative system here. OH, OH, and OH like this. That will become D-xylose. And if you have both the OH on the left side here, except this D family is retained that way, then it is called D-lixose. So when you have 5 carbon, what are the names? Ribose, arabinose, lixo, xylose, and lixose. Okay. Now on the ribose, if it will add one more OH group onto it. Okay. And this time OH is on the right and OH is on the left. If it is OH on the right, it is called D-allose. If OH is on the
Mm.
left, it is called D-altrose. And in the case
Okay.
of arabinose, when you add OH on the right, that becomes D-glucose. So out of the family of 16, when you have 6 carbons, you will have 4 chiral centers. 4 chiral centers means 2 raised to power of 4. So how many number of isomers we will have? 16
60.
isomers. Out of those 16 isomers, one of them is D-glucose. Got it? So this becomes
Yeah.
D-glucose. And instead of OH on the right, if I put OH on the left as a new child carbon, if
Mm.
OH is on the left, then that will become mannose. So glucose and mannose, both of them are derived from arabinose. Arabinose is derived from erythrose. Erythrose is derived from glyceraldehyde. This is the path that you need to remember. Others,
Okay.
that's okay. If you do not remember, that's fine. But this
Mm.
glucose direction is important. Okay.
Okay.
Next, D-xylose, if at all uh, you add one more OH, and this time if the OH is on the right, it is called gulose. If the OH is on the left, it will give something like an alternative form like this, that is called idose.
Mm.
And in the case of lixose, if I add OH on the right, that will become galactose. And if I add OH on the left, that will become thalose. Okay, so
Okay.
total, because we are talking only about the D family, I should get 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. 8 here. When I talk about L family, I'll also get 8 of them. So they all will have similar names, but L name. L allose, L altrose, L glucose, L mannose, L gulose, L idose, L galactose, and L thalose. So that's how total we have how many? 16 such compounds. Clear?
Okay. Yeah.
right? Like I iterated before, this direction is important for us. Okay, how glyceraldehyde from erythrose to arabinose to glucose and mannose we are getting through, that is important. Okay,
Okay.
so this is the one. You started with glyceraldehyde, erythrose, threose. Threose we got
Hmm.
ribose, arabinose. Arabinose we got glucose and mannose.
Madam. Yeah.
Right? Now, have you noticed something? None of them are mirror images of each other. Correct?
Yeah.
Obviously, they are all different molecules.
Hmm.
When two stereoisomers, because glucose and mannose, if you notice, they have molar mass same exactly. Everything is same. Structurally, they are all exactly OH groups, aldehydes, everything at the same position. Only thing that is changing is the rotation. That means it is the configuration that is changing with the new chiral centers. Correct? So I can say that allose, altros, glucose, mannose, all of these are diastereomers of each other.
Hmm.
What are diastereomers? Two stereoisomers which are non-mirror images are called
Yeah.
diastereomers in simple terms. Okay. So if I choose any two of them, they are all diastereomers of each other, isn't it?
Yes.
First of all, they are all stereoisomers. All of
Yeah.
them, right? From all these eight are stereoisomers of each other,
Hmm.
correct? And none of them are like mirror images of each other. So therefore, they are all diastereomers of each other.
Hmm.
Now there is a special type of diastereomeric condition. Imagine if there are two sugars you are comparing and they are diastereomers, but their configuration is varying only at one chiral center. Rest all the chiral centers they have same configuration, except at one chiral center the configuration is different. Then we call them as epimers. We call them as epimers. For example, if you notice glucose and mannose, for instance, OH OH right only, OH
Hmm.
OH on the right only, OH OH on the left only. Now see
Yeah.
OH and OH, one is right, one is left. So that means all the configurations were same except for this chiral carbon. Correct?
Hmm.
That clear? And what is this position, beta? 1, 2, 3, 4, 5, 6. This is how we write the IUPAC.
Yeah.
This is the numbering given in IUPAC, which means
Yeah.
at carbon 2 position only we have the variance of the configuration. Is that clear? And
Oh.
therefore, I would call glucose and mannose are C2 epimers because their
Hmm.
variation is only on second carbon.
Yeah.
Likewise, allose and altros are also C2 epimers. Glucose and idose are also C2 epimers.
Hmm.
Galactose and thallose are also C2 epimers. Done?
Yes, sir.
If you see the set of epimers at C2 with respect to glucose, if you notice, at C2 we have mannose. C4, if you compare at C4, rest all the structure will be same. Only variance happens at C4, then that is galactose. So that means glucose and galactose are C4 epimers. Go back and check here. This is galactose structure. This is glucose structure, right? If you notice structurally everything is same except at
Hmm.
this fourth position, this position and this position if you compare. At these
Yeah.
two positions only change. Rest all are same. So I can say glucose and galactose are C4 epimers. Therefore,
So
mm,
do we have to learn all these structures?
this side is important. This much you have to learn. Arabinose towards these two. Okay.
No, 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 but all these structures, like all these eight structures, do
Not
we have to
necessary.
learn?
Like is it this is one is more necessary part of it. So
Okay. Okay.
glucose, mannose, and galactose. We will not be using these at all. Not in any case. Okay. So,
Okay.
but these three are the most commonly used. So you should definitely know their structures. Okay. Hmm.
Yes, sir.
Similarly, C3, if you compare, it will be allose, which will be in epimerism with glucose.
Hmm.
C5 will also show epimerism at uh, with L-idose. Okay,
Mm.
clear? Now,
Yes, sir.
this is something an introductory of glucose that you need to know. Now, notice glucose has various names. In medical
Mm.
industry, we usually use the term dextrose or dextrin. Okay, and grape sugar usually has more glucose to it. Okay, next. How do we prepare this glucose? Majority of the time, glucose is prepared from either sucrose or starch. So, sucrose on hydrolysis will give you glucose and fructose. Got it? And each will give 1 mole because sucrose, in fact, is a formation of between glucose and fructose only. Starch is all made up of glucose only. On hydrolysis, it will give back the glucose form. Okay, these are two preparation ways. Now, what are the chemical reactions? Glucose, when you react with HCN, glucose is an aldehyde. So now you see all aldehyde reactions only from here on. So an
Yeah.
aldehyde, when you react HCN, what do we get? OH and cyanide we will get. This is called cyanohydrin, isn't it? So this is called glucose cyanohydrin. And glucose cyanohydrin on hydrolysis, the cyanide will convert into an acid group. So this is what is the final product you will have. Okay.
Okay.
Next with hydroxylamine, NH2OH.
Mm.
Again with aldehyde, this oxygen and these two hydrogens will come out as water and they get connected as C double bond N and OH. C double bond N and OH functional group is called oxime, and there is only one oxime which is forming, so that's why it is called glucose monooxime.
Mm.
Okay, so this is glucose monooxime which is colored. Okay, next reaction with bromine water. Now, if you have this glucose, when you react with bromine water is a mild oxidizing agent. It will convert aldehydes into acids. So this aldehyde will convert into an acid, and this acid is called as gluconic acid or aldonic acid.
Mm.
And you see, gluconic acid or an aldonic acid will decolorize bromine water. Okay, it will decolorize the bromine water. So that means bromine water, which is supposed to be red in color, brown red in color, it will become colorless. Okay. Next one is acetylation. Acetylation is wherever there is an OH group, mm, at that position we can convert that with acetyl by making an esterification. So AC2O, that is acetyl anhydride here, this is the compound. And when you treat with the alcohol here, it will connect and this group will go. So what is stuck? This C double bond of CH3 is stuck. So how much molar mass per OH we are increasing? 42 units we are increasing. This we have done it as a question earlier, correct?
Yeah.
So how many number of OH groups are present? So we learned that final molar mass minus initial molar mass divided by 42. That will give you number of OH groups we have, correct?
Yeah.
Same way. So we can connect that C double aldehyde will remain the same, that wherever alcohols are present, they will become OAC. So this is read as glucopentaacetate group. It is called
Mm.
glucopentaacetate group. Got it? And notice this is a proof for showing that there are 5 OH groups present here. So you calculate the value of N here. So this will come out to be 5, which suggests that
Yeah.
there are 5 hydroxy groups present. Okay.
Mm.
And hydroxy groups, if they are present, obviously they all have to present an every different carbon, because two OH groups can never be stable on a carbon position. Okay. So
Yeah.
they'll convert back into a double bond O. Therefore, here, since you are not noticing any of that, which means there are 5 OH groups present.
Okay.
Next, if you treat with 2,4-DNP also, okay, 2,4-DNP also, you can see this is an aldehyde form. Aldehyde form will give you the C double bond N form. And here also you will get a colored, sorry, here you are supposed to get a colored compound, correct? But what
Mm.
happens, you notice you'll hardly see any reaction happening here. although it should give a positive. In fact, it is used as one of the main tests for detection of aldehydes, correct? Aldehydes and ketones. So that
Yeah.
means whether there is a carbonyl group or not, C double bond O group or not, that can be judged based upon 2,4-DNP test. Agreed? But
Mm.
now, when it comes to 2,4-DNP test here, there is no reaction of that sort happening, which means
Mm.
there must be some kind of a different structure present for glucose, which we haven't explained yet.
Yeah.
Next one is with dilute HNO3. HNO3 is an oxidizing agent. It will oxidize
Mm.
aldehydes and primary alcohols into acids.
Right.
So aldehyde will convert into acid, primary alcohol will convert into acid. So both
Mm.
above and below you will have acidic values. So that makes it glucaric acid, aldaric acid, or saccharic acid. All these are the names given to it.
Yes.
COH above and COH below we should have. Then it is glucaric, aldaric, or saccharic acid. Okay.
Yeah. Got it.
Next one. If you react with HI or red phosphorus HI is a strongest or
Mm.
in fact one of the best reducing agent. So it
Mm.
will reduce everything to convert into alkane. That's why all these groups will get reduced and convert into N-hexane. In fact, N-hexane is the way to support the statement that the carbons are not having any branches in glucose. So they're only straight chain. Got it? Next one is an oxidation with Tollens, Fehling's and Benedict solution. Okay. You notice that glucose with Tollens reagent will give you positive test. That means it will become COO minus and silver mirror.
Mm.
And this one, when you react with copper 2 plus, right? This is failing solution that will convert this CHO into COO minus as well, and copper will convert into Cu2O, which is red color precipitate.
Yeah.
And you know that glucose is a reducing sugar, beta. Glucose is a reducing sugar.
Mm.
Okay, what is this reducing sugar exactly means? That means it is able to oxidize the Tollens, Fehling's, and Benedict solution.
Mm.
Clear?
Yes.
Next is the reaction with basic medium or just keeping the glucose in basic medium. Now here is an
Mm.
interesting fact. Glucose, D-glucose, D-fructose and D-mannose, they always found to be in equilibrium with each other
Mm.
whenever you use basic medium. Okay. Now let me
Mm.
explain how does this happen. See, if this is a ketonic group, can I write this ketonic group into enol form? Okay, this is keto form.
Mm.
This is an enol form, double bond and
Yeah.
OH, correct? And in this enol form, if I try to bring back the aldehyde or a keto form, now you can see
Mm.
this side is also enol, this side is also enol, correct?
Yeah.
And when I make this side enol, this OH could come on the left hand side or on the right hand side, correct? So I can get this right hand side or I can get it on the left hand side here. Where is that? Here, glucose, which is on the, sorry, here, glucose, which is on the right hand side, or mannose, which is on the left hand side, correct? This is with aldehydes, okay? Or
Mm.
you can make this double bond to shift here and convert into fructose.
Yeah.
That means if at all I take glucose in the pure form, there is no fructose, there is no mannose, okay? Okay? Imagine I took only glucose and
Mm.
I added some base OH minus and kept it for a long time. You know what happens? Now after some time, you will see fructose is around 33%. This is also 33% and this is also 33% approximately.
Mm.
Clear? That is
Yes.
chances of one to interconvert to other is more, isn't it?
Yeah.
In basic medium. Okay. Because rest of the structure is same beta. The problem comes is only between the first two carbons. See, only the first
Mm.
two carbons has a problem. Rest all the structure is exactly same for all of them. Hmm? And that's the reason why in the presence of basic medium OH minus, this entire group will convert into these three. Done? Any doubt?
No, sir.
Right. Which means, have you
Mm.
noticed something? Earlier I told that glucose is a reducing sugar because it is
Yeah.
able to reduce Tollens, Fehling's and Benedict solution. Now, if glucose is reducing, that automatic, and you know that Tollens and Fehlings are in basic medium. These are all in the presence of OH minus and OH minus here, correct?
Mm.
They are in basic medium. So in basic medium, what should happen, beta? Even if you take fructose also, you will get sufficient glucose and mannose. Even if you
Yeah.
have glucose also, you can get sufficient fructose and mannose and so on, correct?
Mm.
Right. That's why in basic medium, all three can exist. Therefore, fructose, glucose, and mannose all will give positive test with it.
Oh, okay.
Okay. So whether it is glucose, fructose, or mannose, all of them will give you positive test.
Mm.
Clear, beta? Right. So
Yes,
that's what
sir.
I have written here. So fructose, glucose, mannose, all of them are reducing sugars. Okay. Last thing is reaction with NaBH4. If you notice, NaBH4 is a reducing agent. It will convert aldehyde into alcohol. So now you will have all 6 carbons with OH group. And all 6 carbons with OH group is called sorbitol. It is called sorbitol or alditol.
Mm.
Because it is derived from aldehyde, we call it as alditol as well. Next, reaction with concentrated H2SO4. See, glucose, fructose, mannose, they all will get easily dehydrated because there are, lots of OH groups. And as it start dehydrating, eventually you'll only left with carbon black. That's why glucose or fructose or sucrose, everything when you add it to concentrated H2SO4, you'll start seeing vapor. First, you'll start seeing steam, which is H2O. H2O vapors will start coming across, and along with that, the burning of carbon takes place and it will convert into a black soot.
Yeah.
Got it? So that is what happens with concentrated H2SO4. Then next, the next reaction is with phenylhydrazine. Okay. So if I take 3 moles of phenylhydrazine, then glucose is found to have like this. So this is glucose, and when I take 3 moles of phenylhydrazine here, so H2 from here and O from here can be relieved, and you'll get this product, correct? And likewise, it can happen on this position also, and it will happen on this position also. See how does that happen? Okay, as a mechanism, I'm giving you this step. Imagine the first one happened here. When the first one happened here, then the O minus which is present on the second position here, because uh, while coming out here, when you get this as O minus here, because you are making it as C double bond N NHPH, correct? So this OH here will convert first into O minus, and that O minus will push into double bond. The H minus will shift onto this nitrogen.
Mm.
That way the aniline part will be removed out. So this is how the aniline part will come out. Okay. This is the aniline part which you will left out with, and therefore C double bond N, clear, and this hydrogen going on to nitrogen here. So you will get this as C double bond NH, C double bond O, and this one. Clear? So
Yeah.
one thing that it need to be noted that now C double bond is come across second position, because it is on second position. Again, the addition will take place. So therefore, on second position also we'll have C double bond N NHPH. Got it?
Yes, sir.
Right. Therefore, this compound first you will get C double bond NHPH, C double bond NHPH on both the positions, and this compound will appear like a, uh, as you crystallize it, right? It will
Mm.
have a colored crystals. It will start forming colored crystals here.
Okay.
Okay.
Yeah.
So therefore, this is called as osazone. Okay.
Mm.
This colored crystals, what it forms is osazone. Again, Ozone has something to do with the first carbon and second carbon's attack only, isn't it?
Yeah.
So therefore, again, if you notice glucose, fructose, and mannose, all three should give you same ozone.
Yeah.
Clear? So
Yes,
this is
sir.
the same ozone form. Next, what is the reaction with HiO4? So this is the glucose structure. If I use HiO4, we have discussed this in alcohols. You just have to
Mm.
start breaking the bonds, correct? Because
Yes, sir.
wherever you have a vicinal diols, you break the bond, keep one OH above, one OH below. Again, you have here OH and OH. So break the bond, one OH below, one OH above. Again, break the bond, OH and OH are present. So one OH down, one OH up. Again, OH and OH are present. So give one OH down, one OH up. Again, one OH and aldehyde is present. There also you can break the bond, keep one OH up and one OH down. As you give that, carbon having three OH groups, that will convert into acids. So how many we
Mm.
have? One, two, three, four. These are all acids. And here C double bond is already there. One more OH will only make it acids. So therefore, how many acids will get? 5 moles. So you will get 5 moles of acids and 1 mole of aldehyde. This last carbon will be in aldehyde form. Okay. And this is one example where you can see how many number of moles of HiO4 is being used. Got it?
Yes, sir.
Any doubt here, beta?
No, sir.
Right. Okay. So this is the first part of biomolecules which we need to learn. Got it?